Okay, modulus of rigidity and then stress strain curves. These are things you're going to prepare for your test 1. What is structural analysis or structural engineering, or the engineer does? Engineers do. A structural engineer begins the structural system, structural elements, buildings, bridges, stadium, tunnels, canals, and other civil engineering works. Right? These are all the design is the backbone, right? And your analysis is the backbone of design. No analysis, design will be failure. Design supported by analysis. Coming to design, it may be process of determining location, material, size, structural elements to resist forces acting in a structure. It might be location, where the maximum, where the minimum, material, come out with the diameter, come out with the Young's modulus, come out with the Poisson ratio, come out with the, what else, your properties, factor of safety and so on. And then size of the structural elements, it may be what is the diameter at the end, what is the maximum diameter, what is the optimal size of the cross section and so on. To resist, this is structural elements to resist forces, and it may be size or it may be the maximum stress, maximum force required to withstand the more maximum force borne by the given material or the size and so on. Like this bridge, all these bridges are analyzed and then only built. No analysis, it may be a failure. You have to see all the scenarios of its design, then it is easier. Design process in structural engineering will be like this. Determine force, and I'm combining all the 4 slides which are used for these 2 chapters. Okay, there's a brief information about that. Determine forces acting on a structure is important. Determine appropriate structural system for a particular case, right? Yeah. Having given the load, you should decide, right? You should decide what are the combination of load, whether the bungalow type building can have. Later I show my FIP student work, a very good work. You've done a very good work. I will show you. I will ask him to record it. With his permission, I will share with you the modeling. He has used Revit, StatPro, and ETAP. You can compare. The purpose is to compare, because quite often student confused with which analysis software have to be used. Whether StatPro, ETAP, there are limitations. There are few limitations, and this work, the work done by the student, will be very helpful for future student to know which one to use and which conditions we can use. Like that, when the structure is given to you, you should know the combination of loading. Later we'll see types of load. With that, you should know which combination, whether the 2-story building, just live load, dead load is enough. When you grow with the tower building, must include wind load, earthquake load, and wind load, what type, seismic load, what type. All these things are to be analyzed before you go for design. That's why the package and the case, which particular case you have to follow. And then select material for construction is most important, right? That saves money, right? That's the most important job of today's, in pandemic time. People are finding the economic material, right? And they're comparing now whether human intervention can be reduced by IR4. When they implement IR4, it's an initial investment, huge initial investment is required. But when they calculate over the period of time with the manpower, when it is replaced with the manpower as in the traditional way, it is going to gain a lot. So they calculate, and every company is venturing in converting to IR4 or all automized system. Start from procurement, start from planning, start from procurement, go to the site. Like 1:10 will be started with 1:10 people are employed to do this job, and the 10 people effort, the expenditure on 10 people effort is being turned to be invested into automation. That's how companies are growing. You should also grow in line with that. Recently, I'm also arranging one seminar on how to do the automation in structure, another one on environment topic. Please attend those seminars and to get start to learn how to do that. And later on, there are so many online courses with certificate, without certificate, you can gain a lot, right? The only thing, you have to have dedication. You have to have focused learning habit. That is important. With that, you can achieve it. Now coming to this one, material. Yeah, economy. You have to make it very economic by using proper economic material, not spending more on the materials. Materials also playing a role, and for the particular uh, element of the building. Calculate size of the members and connections to avoid failure or excessive deformation. Yes, this part is the most important thing that stress analysis is playing. Stress analysis is important. Analysis is important to avoid failure. Find out where is the failure, where the material didn't respond, where the stress distribution is poor, cannot withstand, cannot match, cannot compete. Then you analyze the member by using stress analysis. Um, Stress analysis methods. Right. Coming to force. Is that okay? I go by these slides for your test. Are they okay? Very simple. Let me finish and you tell me. The forces acting on will be, and some of, I mean, similar, some of the slides are also there, but I mean, summary of those slides are here. Forces induced by gravity, forces induced by wind, forces induced by earthquake, forces induced by rain and snow, fluid pressure. You have to add one more, huh? What is this? Signal. You know, the signals, the signal shot. I don't know how the origin is still not predictable. You may have to add the signal, effect of signal also can break the bridge, break the canal, break the system. So that type of loading, the shock, the shock, it is a shock. It is not rotation, it is not bending, it is not a compression tension, but a shock to the building, right? Shock to the building which can collapse even the molecule and atom of the building has to be studied in future. You may take it that is coming under nanotechnology, you know. Nanotechnology area is booming up in environment, water, construction, chemical. Nanotechnology is booming up. You can take up nanotechnology material in construction to do your further studies or research, or your when you go to job also you can recommend such projects. It saves you money. Through that you can identify. There are things, studies going on, but we am not much into that area. Okay. But this list is not stopped. It is not just 1, 2, 3, 4, 5, 6. 6 is here due to electric shock signals, electronic signals. We do not know which one is it. So these types is also coming up. About um, six types of loading are there. And this gravity load of two types, dead loads are due to, this is the self weight of the building itself due to other objects, right? Moving objects, stored objects, running objects in the building, or occupants, by all occupants. Right. Forces acting in structures. Okay, gravity force acting this way. Direction is important, right? Stress analysis, direction is important. And point of action is important. Vertical, gravity force always act vertically, and lateral force acting in this direction. Examples of wind and earthquake. Signals also maybe like these or like these or like this, any type. Normally they have thunder, arresters, lightning arresters on top of the house. With that it is still okay, until today is safe. But if it is running water, canal, bridge, we cannot control. There's always already a conductor at the beneath the bridge, so we cannot avoid it. Right. See here, this is vertical and this is horizontal. Should know the direction of forces. Matter for analysis. And then coming to global stability. Due to this type of lateral loading, it might be a sliding or overturning or rotation, right? Sliding, overturning or rotation. And then failure due to axial load on top, right? Axial load on top for the fixed end may be like this, the dotted lines. What may be the failure for this type? When the moments or couples are acting at the ends, what may be the shape of the bar after the application of couples at the end? What's the name? Come on, answer me. What's the name of the failure that is caused when a couple is acting at the ends? of the bar, which is fixed at N. What is the name? Anybody? Take it sportively. You do mistake also, no problem. Correct here. What kind of failure is it? Quickly.
Change.
Huh? Hmm? If the couple is acting, what kind of the name term, English term? You verify, you check and tell me in your slides. It is there. Typical structural system.
Warping.
Very good. Warping, huh? Warping. Is this common for all types of cross section? Next question I will ask. Is this common for all? Warping is there for all cross section like circular, rectangular, triangular, trapezoidal. Again, please answer. I will correct. This is how you have to learn. Don't hesitate. Think and answer. Unmute. Is this common for all type of sections? So you may be good at calculation. Some theoretical point, basic things you also should be in mind. Principles to apply, to shoot, troubleshoot. That is why it is tested. Last time I gave all 10 questions as objective to learn more. This time I change it because you are good at calculation. It's changed to this. Please tell me, is it same for all sections? Anybody? Not only Martin answering, 1Y answering or Lamso answering. Somebody have to, all have to participate. Need more time? Imagine la cross section. Warping means what? The cross section, when it is twisted, the element, each and element, if you follow, will be different. The shapes will be different, isn't it? On the surface. On the surface, take rectangular or square. When you turn it, it will become rhombus like that, isn't it? Rhombus. But the shape, when you take the same shape, it is totally different because it has sharp corners, 4 sharp corners. A rectangle also some corners are there, edges are there. Trapezoid also edges are there. Based on the edges, it may turn to different shapes. At any cross section, if you cut, the cross sections are not uniform. One cross section will be big, one cross section will be small, one cross section will be, and so on. On the other hand, when you twist the circular section, it's peculiar to circular section only. That two application is only axial. This is axial. Other cases we are not discussing now. Only axially applied couples. When you twist the circular one, cut all the places, it will be same because there is no edge, smooth surface. All become rhombus of same size or equivalently. All are rhombus of more or less similar shape and size. So warping is not occurring in circular section. Except circular section, all other cross sections are subjected to warping, meaning the cross section, individual cross section are deformed. When the couple is acting, when the ends are twisted, the cross section, individual cross section are not similar. On the other hand, circular, individual cross section is similar. Only thing there is an inclination. The points are inclined on the same, maintaining the cross section. Like diameter is 6 means until the end it is 6 only. Unless you really apply a very high load to let it fail, right? But for an equilibrium system undergoing, whenever you design, you will design for an equilibrium system, right? Whatever the application of load should be bound by the material or the system. In that case, warping is not there for a circular section. Okay, it maintains the cross section. Right. Typical structure system, this one, arch. In these following slides, you may have to answer whether it's a compression or tension member, like this. Typical structural system. This is arch type, right? This arch type, when the load is applied here, all the load is distributed to the support, right? Is a compression or tension member? Compression loading acting or tension acting? Can you imagine?
Tension.
Tension at which point? You understand what is tension and compression, right? Compression means reduce in cross section, reduce in length, and then compression, increase in cross section and reduction in length. In this situation of loading on ores, what will happen is a compression or tension. Must be compression, right? It's going to reduce. It is going to reduce or get compressed. The length, overall length, if you measure after application of the load, it will be, because it is fixed at the end. If no fixed at the end, there is a chance of flexibility, bit flexibility on acting on it. And then this one, there are all types. Here you can see all types. Typical structural system of all types. You see here carefully, bigger the size. See carefully. On top, this is the compression member. Typical process when due to this loading, how the load is distributed. Take one sample, right? Take one sample. When you take one sample, the compression will be acting on this member because horizontal, and then tension will be borne by or supported by, right? Tension will be supported by this crossbar. Another compression, another tension because at the bottom, and this one is compression. Okay, when it is compressed, with a vertical load acting, right? Gravity is more, so try to, the verticals will be, verticals on top will be compressed, bottom will be elongated like this, bending. So the ring is there. See here, the profile already given here. You can also follow the profile. Because of the profile, this is compressed, this is tensed. This is compressed and this is tensed. This very basic thing. You don't have to worry about much now, but understand where the compression by imagining how the member will behave. Where is the compression? Where is the tension? That's the point. To take up the tension only, they put the crossbar. You remove these all crossbars, all get bent already, or compression will be more. To support this compression, they put the crossbar. Or take up the tension, they put the crossbar. Why the crossbar? If it is horizontal, again subject. If the same thing is horizontal, subject to compression, because it has some inclination, it may get elongated rather than compressed. A bit of common sense. Unless I show a demonstration, this cannot be understood. But you have to have an imagination, right, at the point and direction of, and the location of the member, and so on. Next one. Typical structure system. Come on, this is also, just understand where is the compression, where is the tension. See here, the load is acting on it. These are all for theory, which we already done, and I repeat once again here, but I touch upon in the beginning of the session. Have put additional slides for you to understand more. When a frame is subjected to loading on top, what will happen? Right? Suppose it is fixed. Assume that it's fixed. What will happen? This beam, as usual, that just now we saw also, will undergo a profile of deformation will be like this, having compression on top, tension on bottom. And this one, because it's fixed here, and there is support in between, it will tend to rotate like this. If no support, it will tend to bend like this, right? In general, because again depends on the standard ratio that you will study in the last chapter of columns, buckling of columns. Right now not important, but have some imagination only. When the load is applied, there is a compression on top, tension at the bottom. In this case also, compression on top, tension at the top, compression at the bottom. When you look at from here, it's top and bottom. And this case, because this member is in this supporting in this direction, right, it will not elongate. So it will only bend in this way, having compression here and tension at the bottom. So it's all common sense for identifying the member only. Calculation, you really didn't need a analysis, but in this case have to imagine how the member will behave. And then coming to this point quickly, I want to do calculation also. If not, I just post you go through the video. Calculation also important. Definition of stress. All of you know is force over area, right? Force over unit area. It may be of shear stress, compressive stress, tensile stress. Here, what type of stress is explained? Anybody? Answer me. What type of stress is explained here?
Tangent stress.
Tensile stress. Very good. Tensile stress. What kind of parameter we can identify? I mean, what is the modulus of which modulus is governing this type of problem in designing? Which modulus is used? Modulus of elasticity, isn't it? Young's modulus of elasticity. Okay. What is happening? This is original length. After pulling, extended to some distance, right? Come on, now define strain here. Anyone define strain here?
Change of length divided by total
Not
length.
Martin, and next time you should not answer. Thanks, Martin. You don't have to your friends. Next time the question goes to somebody. Okay. Thanks, Martin. Now, next question is the strain dimensionless or not? Simple questions only. Is the strain dimensionless or not? Strain. Khalif, didn't go to the attendance. Huh? Is the strain dimensionless or not? Take it sportively, don't worry, it's after all from among your friends and classmates. It is not going to determine your knowledge or give you grade. It is for practice. Take it sport. What happened to 4 people? 4 people absent today. I don't know. Come on. Why 4
It is a
people?
dimensionless.
Very good. Because change in length by original, both length, right? Very simple answer. Right. Thanks, Khalif. Next. Simple things you have to remember. Now, so if you're asked to calculate the strain, you can find out, right? And then what is this? Can you write the definition for strain here? Anybody? No, E. What's the definition? Oh, it's already there. I thought of removing it. Okay. What is the definition of E? Read from the slide. What is the definition of E? Modulus of elasticity is a ratio between stress over strain. What is the unit for modulus of elasticity? Anybody? Modulus of a unit for modulus of elasticity. You know the definition now, stress over strain. What is the unit for modulus of elasticity? Why is not running? What's the unit?
Pressure.
Louder, please. A bit louder, please. What's the unit of modulus of elasticity?
Pascal.
Yeah, very good. Because no unit for strain. Strain is a percentage or ratio, I mean number, because the ratio, dimensionless, you live with the unit of the stress. It is all there in your slides also. Come on, let's understand more about this behavior. Stress strain behavior. Stress versus strain is a linear. Then we call this as a elastic. There is an elastic region in your stress strain graph. After this is a non-linear or transition region. Transition is explained here. Non-linear elastic. No, the same elastic may be a non-linear. Okay, what material is it, and what material is it? And then coming to plastic strain, it may be a plastic strain. It is right from the beginning. It may be like this, and then immediately drop down. It won't no longer maintain a what do you call a straight line. Let me finish this also. Non-linear plastic, very bad. Once it finishes the elastic limit, broken already. With this itself broken already. Come on, give examples. Start from here. Any example material for this one? Number one, linear elastic. Think. Mild steel, all steel material. because we did the test using a steel rod. So steel materials mostly follow this one. They are proportion for some time because the ductility is good. So they will have proportion between stress and strain to some distance. What about this? Starting itself elastic, not in proportion, meaning what? For a simple load, take here a small load point. For a small load itself, it is changed to, I don't know, I only hand. For small load itself, take this point. Instead of being here proportionate, the load is very high, but the strain or deformation is very low, right? The load is very high, the deformation is very low. Which one? Bit harder than steel, right? Whatever bit harder than steel, at the same time not very brittle in nature, but in between. What is that material? See here, the proportion is like this, non-linear elastic. It is all there in the graph in your notes. Even the table also I have given different materials. So what is the values? Values also given. Based on the values also you can classify which material will behave linear, non-linear, elastic, and non-linear plastic. Come on, what is the material for this one? Refer the diagram or the table and tell me. Non-linear elastic, because it is elastic. Yeah, it has some region of respawn. It will, once you remove the load, it can get back to the original shape. That is what elastic, right? And here there is a clean straight line. Whenever you remove, it will clearly come back. But in this case, when you remove, the deformation is very low, not like this one, very low. Quite tough, bit tough material, so that you can bear more load with a less deformation. Quick. Just make a guess, I will correct it. I leave it for you to study. Okay, I give some time. The next one will be, okay, I finish all, then you answer me. Maybe give more information on this. The materials used in the, you can base on this also. These are the materials we are using in your civil engineering, right? Stone or masonry, right? It can be a wall, it can be a stone, hot stone, or metals, cast iron, steel, aluminum, and concrete, wood, and fiber reinforced plastics. These are the materials. You just think of this material and try to match with this graph. Okay, I leave it to you, and then you can correct with me if you have doubt. Come on, this one. This you have to have some idea, right? Being engineer, and you, if you do FYP project in future, you cannot always refer to the material or a code book or manual or CD or floppy or a pen drive. You should have remembered the values roughly. That's why it is brought separately for you. Maximum stress, this is 250 to 1000. Can go up to 1000. If it is a bit alloy material, a mix of material, or the ore is from different region, based on all the testing and experimentation, they come out with a saying that it can go up to 1000. And then strain, maximum strain it can bear is, see the ratio 20%, 40%. Failure is 20 to 40%, nearing half. And concrete, maximum stress is, see, concrete 30 to 120 megapascal. Cannot go beyond that. Cannot go beyond that. Very less compared to this one. Or it's other good in other way, right? Maximum strain is very, very poor. Cannot get elongated. Immediately breaks. Cannot elongate it because cannot take more tension. Compression can be taken. So breaks immediately with the strain of this much. And then load itself is, I mean, stress value itself very low. Wood values depend on wood grade. Yeah. Different types of wood behaves in different way. Bamboo, balsa, timber, and then what else? Different types. Okay. Below are some of the examples. Tensile stress is 10 megapascals. Commonly, common wood in an average should be 10 megapascals. Compression can be again 10 megapascals. So here all they are all different. But here in this case, wood is behaving in the same way for tension and compression. I think that's all. Have some more. Last slide. One moment. Answer me how to determine maximum strength in a member. I put all the questions already. Come on. How to determine the maximum strength in member? You keep thinking, and then you have to answer. Come on. When you analyze, you can analyze this way, right? You can analyze this way. I mean, these are the output from the. Forgotten the software. How did I read for you? Forgotten the software name, but software ETAB, right? ETAB, and then Revit, ANSYS, they're all printing the results in the colored form. Depending on, see, they have the scale also here. It's not extending at all. Huh? The scale, this is showing the scale from low to high. From low to high, the red areas are the prone to fail. This is high, this is low. So if I arrange it from low to high, they will have high to low. When you analyze, it will automatically printed and you can address those issues. Having design, you test it and see where are the critical locations of failure. Accordingly, you redesign and reanalyze and then make your structure perfect until it is all safer zone, like all green, all blue. Okay, this is one of the output from the software. Now, the plane, the structures, structures can be cross section can be of this, this. And the lower, the elements can be right. You can analyze the element. If this is the body of the ship or body of a submarine or body of the aeroplane, aircraft, you can analyze what is the stress acting on the surface by taking an elemental area outside and then analyze it. We are now doing only the plane stresses, okay, the stress that is acting, because the plane is not always in the same position, rotating, inclined, right, and incline, alighting, up, or taking, right, lifting up. All these situations, it should be maintaining the stress differences. Hence, the engineer have to have the control on the stress variations of different orientation of the object. All this thing can be analyzed using the software. I stop here. Any question you can ask me. If you don't have question, I move on to do calculation. Any question? Two calculations are there. You can study from there. Let me share this. Any question?
Miss, just now the non-linear elastic material, is it the example can be concrete?
The second one, non-plastic, non-elastic.
Non-linear.
And non-linear elastic, right?
Yeah.
Non-linear elastic cannot be concrete because concrete is not at all an elastic. You match with your table, it is there in your class notes. You match the table, you will find out. The values also have given already, strain value, some guideline. Come on. I put here, yes, yeah. Okay, started. All of you open your laptop. Please open your laptop. It's not laptop. A paper, pen, calculator. Come on, get ready. You have to work along with this calculation. Otherwise, the purpose is not solved. Please work along with this. You have the question already. I'm just revising, redoing the calculation with some explanation, more explanation for your review and revising the things. You please start working along with this. Otherwise, you will not do it. Then and there I will ask what is answer, then you answer yourself or check your answer after I give the answer for you. That is how you have to work. It's a practice. All of you ready? Paper, pen, calculator. Come on, if you like, you please switch on your camera. I will take a snap. Otherwise also fine, but please work. I believe you are working. After test one only, I come to know about you. I know you're all good student, but I want to know every day how you are progressing. Okay, let me share. Thanks, Khalif, for sharing. Okay, so I started. I hope you can see the screen. One moment. Why is not sharing? I didn't put the sound. Come on. If it is taking time, please bear in mind. Finish and then you can leave. Okay, it will take a bit longer only because we already taken much time for theory. 1.5 hours is not enough for classes. You're given with the member connected by two parallel members AD and EF, EG. AD and EG. See here, there are two members AD and EG given to you. They are connected by two links. They are interconnected by two links to be in a position and like this, and is being loaded by 24 kilonewton at this point at G. You're asked to calculate how much is the factor of safety to be determined. Okay, how much is the factor of safety should be determined or followed to have this much loading, these types of links and these types of members, and the pins. See here, pins at A, pins at B, pins at E. It is connected by pins. This is not fixed all or pin join. That is important for you to remember. It's a pin join. There is no fixity, so it is free to move. You have to take into account accordingly when you calculate your moments and others. Okay. In this case, how are you going to solve for the factor of safety? You are asked to find. Having given these sections and all, I have already done. If I cut here, okay. If I cut here, the cut section at this point, say XX, will give you the dimensions like this. Section at XX will be a rectangular one, right? A rectangular one. The member cross section is rectangular with a 40 mm depth and then 10 mm thickness, perpendicular to the file. Okay, perpendicular to the sheet here. You can see 10 mm, 40 mm. You can see very well, right? So, what else given to you? Rectangular cross section at this point, and then ultimate strength are given. What is ultimate strength? Quickly, due to the material, right? It is the ultimate strength here is referring to ultimate strength is referring to strength or stress. Both units are same. Or stress is referring to the material property. Okay, material property. How much it can bear the load. What is the allowable? What is the maximum strength that it can bear? If you see the stress strain graph, ultimate strength is the strength at which until then it can load, after which it will start breaking. At one point it will get broken. So this is the ultimate strength of the members are given. This is steel, okay. This is also steel. The pins also steel pins, and the ultimate strength are given. The strength in tension is given for the member 400, and the strength for the pin also given in shear strength. Shear strength for the pin also given because the pin is undergoing a shear stress. So the value of the bearing or allowable is also given as 150 megapascal for the pins. Okay. You are given these values and asked to calculate what would be the factor of safety with this condition of loading. They are supposed to load this much with this strength. Okay, with this strength, what would be the factor of safety to have a successful design? No failure, no breakage, right? Given data quickly before solution, you need to write the given data. Given data are you are given with number 1, the strength, ultimate strength, right? Ultimate strength is ultimate strength or stress. You can have it as ultimate strength or stress. I keep it as it is in stress, right? Ultimate for the pin, right? Pin and the link, okay? Link and the pins are given to you. Let it be L, link. Right, link. Ultimate strength of the link is given as 400 megapascals. And then ultimate strength of the ultimate strength of the pins are given as pins are given as 150 megapascals. Always read the data twice. Your questions, your answer starts from there. You can directly take the answer from there, right? It is like mathematics. Mathematics also, you read the question, the answer is there in the question itself. So you are given with stress itself means half of the question and answer is given to you already, right? Stress is given, and then you need to know how much you can apply. All of you know you are asked to find factor of safety, right? Check whether you have all the formula and the required data for you to solve. Solution, that's all right. The section written already. Number 1 is a section, right? Number 1 is section. Number 2 are the strength is given to you, and then anything else? Diameter of the pins are given. Okay, diameter of the pins are given. Pin, I put the diameter as a 5. 5 referring to the diameter of the diameter. Pin is 20 mm. Remember, okay? The pin circle 20 mm diameter. Okay, and then this is pin. This is pin. This is link. What else? Connecting horizontal members. Okay, these are the conditions given to you. You need to solve for factor of safety for these two, right? Okay. Required answer will be, you also can write the required answer so that you can have a solution done properly. The required answer or the solution will be, you need to find factor of safety for the pins, factor of safety for the links. Okay, how much this and this, okay, put together in this frame, how much is the value for links and the pins. Okay, what else? Should be clearly written. How do you define factor of safety? We go from the question. Determine the factor of safety. What is the factor of safety formula? Solution. Solution started here. Factor of safety is defined as. Factor of safety is defined as. Factor of safety is defined as. It's not taking in. It's in touch mode, right? Okay. How do you define factor of safety? Anyone? How do you define factor of safety? Is equal to?
Strength divided by stress.
Ultimate is the material property, and that should be very high. That's why you put it at the top. Ultimate stress. You check whether I'm doing correctly or not. Allowable or applied. I can say allowable, applied. Ultimate to apply. Let it be applied. Then easy for you to understand. It is going to your apply or going to work on this design. Ultimate to applied or allowable. Okay. Ultimate stress to applied stress. Apply means it is going to come over the future loading. Better keep it like this. Otherwise, you cannot differentiate. Allowable is a bit confusing. Right. This is the definition. So you are given with this answer. You don't know this, right? What is the stress acting on this member? Because you are only given load. Stress need to be calculated. Stress is load per unit area. So take the point of interest, calculate the stress, so that you can calculate the factor of safety, right? You don't know this, you don't know this, but this can be found by given data to do, right? Let's draw the line sketch so that is easy for us. Our point of interest is are the pins and the CF and the pins, okay? at this point. So just draw that line diagram only, line sketch or free body diagram, so that you know where you, what are the loads, what are the reactions. Free body diagram. What do? You can take this member because you are finding for the load is applied here, and for this link, okay, you can translate C to F. When you do that, it will be like this: member E, F, and then G. Keep the same name: E, F at 0.4, G at 0.25. F at 0.4, G at 0.25. Okay, G at 0.25. 0.25. All meters, am I correct? Oh, meters. I changed to meters only. Right? These points we have done. Again, pin. Remember, this is pin. Don't forget. And then C can be translated to F, B to E, and then loading G. Loading is G. I do it in a different color. It is applied with the loading 20 kilonewton at this point, 24 kilonewton at this point G. Okay, G is subjected to 24 kilonewton. Okay, what else you have? Right. Anything else to mark? When this is subjected to loading and there are pins, right? Here also pins. Pin. It is a pin. It is a pin at this point. It is a pin at this point. It is a pin at this point, right? When it is subjected to loading, automatically there will be a reaction at the pins, isn't it? Vertical reaction at the pins. What will be the direction of reaction at this point? It will be vertically upward. It will be vertically upward like this. Reaction will be developed due to the loading. Reaction will be developed at F. And then E is also, but let's see how we are going to do it. And then what else we have to mark? That's all, right? We don't know what is the type of reaction here at E because, see, technically speaking, when you pull this point by a loading, when you pull at G with the loading, it will react in opposite direction to withstand or restrain the loading, resist the loading. At this point, due to pin at this side on both sides, right? It is pin this point, at this point it is pin here and also here. Due to this, it may be upward or downward, we do not know. But you can assume initially and then solve, you will get the right answer. Okay, let it be like this. And then let's find out the reaction, right? We need to find out the reaction because we don't have the, we just have the loading. We want to find out the stress at this point. Stress at this point. Hence, I need to know the loading at this point. Am I right? I don't know the loading. If I only know the loading, how much it is reacting, and then I can calculate the distribution of the stress at F so that I can find the factor of safety at F. These are the unknowns here. Okay. Okay. Who is jumping here and there? Right? We are here. How do you find the force? We can resolve the force above E, right? This is the pin. To find the unknown, either you take G or E, but I want to know how much is the reaction at this point. So I need to make use of the loading. Let's take the point E, okay? Resolve the moment about this point, section E. So when you resolve the moment about E, by equilibrium conditions, all the moment at ME should be equal to 0 because of pin joint. Taking this criteria, let's resolve all the moments about E. Start from G, 24, right? 24 is how much? Positive or negative? 24 kilonewton, positive or negative? will change to Newton. Positive, right? This rotating this way. Keep the clock means it is rotating this way. Many times I done this. So positive, and then going to F into what is the distance? Moment. We are taking moment, right? What will be the distance? This is the force times moment will be 0.65 from here to here, right? From this point to this. From this point to this. We are resolving about E. So we will have into 0.65 meters, and then I've done for G, then F. F will be positive or negative? Negative. That is our unknown, right? So it will be force, reactive force, let it be FCF. For CF, I'm taking FCF. The reaction be FCF. FCF times, how much is the value? Into 0.4, simple. 0.4, clear? We have done for this unknown equal to 0. How much is the FCF value? I want somebody to answer. Hongxian. Hongxian is there? Please answer me, how much is CF? Hongxian. How much is the value of CF in newtons? Get me in newtons? Newtons. Right. Moving on. We found the load. Now we can find the stress distribution or strength. How much is the strength value? Either you can calculate by the strength or by loading. Right. Newton done. Based on tension links. Based on tension links. Next is the we are going to find. We just found the unknown. How much the load at this point? Now we can conveniently find the factor of safety because we got the loading, we got the strength. With this applied force, with the allowable strength, we can find it. But allowable, you need to what do you call here? Where is it? Name this one. This is our ultimate, right? Ultimate strength is given, but you have to find out the ultimate load, right? Because we want to compare between ultimate load to ultimate allowable load. Okay, let's find out. Are you here? Clear? One answer is found out. This is our ultimate. The stress and the loading at load at this point. How much is the ultimate load at this point? At this point at AF, okay, at AF you have two things. One is the link, one link, which is CF, correct? CF and the pin. You need to find separately for the link and pin. Okay. For the link, let's do one by one. For the link, we find separately the factor of safety. Okay. For the link, you can calculate the factor of safety like this. I repeat the sentence. Factor of safety. For load is equal to stress integer. We found out the applied load at this point. Okay, ultimate load is equal to you are given with ultimate stress, right? Ultimate stress into, I have to have some space because stress is equal to force over unit area, isn't it? Force over unit area. Now you are given with stress, you can find the force. Load is equal to stress into area, right? Load is equal to stress into area. That is what I'm doing here. So ultimate stress, ultimate stress times area at link, area of the link. We are doing first for the link. Okay. Let's find out the load. You are given with ultimate stress. How much is that? Later we substitute. Let me find area of the link. Do you have area of the link? Don't have, right? You need to find the area of the link first. Alright. How much is the area of the link? Let's find out area of the link. In this unknown is area of the link. Take the cross section. Just now we draw, right? The vertical cross section. I draw. Say got a pin, right? How much is pin dimension? 20, right? So I need, so the area that is contributing to this, the area of the link that is contributing to this will be this much, isn't it? This is the value of the area that is contributing to the loading. So I have to deduct this value area is equal to area of the link. Area of the link is equal to B minus D. B minus D into D. B is where B is the 40 or D. Let it be this one. This is for the link. This is for the pin. Okay. I put it as D itself. Easy for you. Depth of the link to depth of the pin. Depth of the link is given by 40, which is 0.4 minus 0.04 because mm 0.04, and then for others, how much is the value? Depth of 10 mm, isn't it? 0.02. Clear? We have done this part, and then times thickness. Thickness of the, you see here in this view, you can see clearly the cross section. I already drawn here. The thickness is 10 mm, isn't it? Thickness means this portion. The thickness of this one is 10 mm. 10 mm. So here if you want to see this thickness times the depth, okay? This thickness times the depth is important. This much depth of the link is contributing to this load and the stress distribution. Hence, you need to calculate the net value that is also contributing to this stress distribution by deducting the pin. That is what I draw the cross section here. It will be times 10 thickness of the link. This is the area contributing to this stress distribution. How much is the answer, please? Give me the answer. What is the answer? Are you following? Any question? Guys, any question you have? Following, right?
Yes.
Doing. Okay, good. Let me continue. You don't have this value, right? You need to find this. Okay. Ultimate stress is equal to, or I keep it as 1. Substitute in 1. Just continue with this. Okay, our ultimate times the area. How much the area we found out? 200 into 10 power minus 6. And this due to the, because we are asked to find out the for the whole system, right? For the whole system, how is the overall factor of safety? For the whole system, how is this? Because the response here is due to response of this and this link, right? But you are asked to calculate at this point. Hence, you need to multiply by 2. 2 links are acting at this point. Hence, you need to multiply by 2. It's the response or reaction due to the 2 links. Because of the 2 links are double links, you have to multiply by 2. What is the answer here? Let's move on. Now we found out the ultimate load for this one. Can you find the factor of safety now? We have the load, ultimate load, applied load. Okay, 2 gentlemen are here already. Can we find factor of safety? Factor of safety. Safety, mind the spelling. Safety at the link. At the link is equal to formula ultimate load, because you all have load only, right? Ultimate, why am I highlighting that? Times 10 power 3 divided by applied load is 39 times 10 power 3. Come on, get me the answer quickly. You got your factor of safety. Factor of safety for your links. Same you have to repeat for the pin. It's a sufficient amount according to the load. You can remove the link or bearing 4 times that applied. Only 39 is applied. Your member can bear up to 160. 4 times bigger you are designing, over design. Okay. Then you can adjust accordingly to remove the link, and find out, put an sufficient amount according to the load. You can remove the link or relax the pin and so on. You can do it, right? Next category is this is for the link, right? Next is for the pin. Same you have to repeat for the pin. For the pin, factor of safety for the pin, all the calculation analysis for the pin. Okay, can you repeat the same? Ultimate stress square by 4. pi d square by 4. Area of the pin. So whole pin is in action for reacting to the load applied 24 kilonewtons. Pi d square. How much is d? Diameter is 20 mm. Square divided by 4. What is the answer? Is equal to anybody? Area of the pin?
3.14.
Power minus.
Okay, 3.314 and 314
times 10 to the power of -4.
-4. No. Anybody? Wrong answer. Negative.
6.
Be more careful. I will ask is 150. 150 megapascals. 150 megapascals times area, right? Area is how much? This one, AP naught. I substitute the value itself. Convert the value of megapascal, everything you convert it into 10 power 6 pascals, Newton per meter square, you got it, into the value of what is it? Area 3.314 into 10 power. You put the points, everything. Okay, put the points. 3 point into 10 power multiply by 2. Multiply by 2. Okay. Answer. Give me the answer for the pin. Ultimate loading at the pin into 10 power. Anything is there? Yeah, 10 power 3 newtons or kilonewtons. You can put it either kilonewton or newtons. 3, because otherwise gentleman is applied load. 13 is already your applied load. Same goes to pins. Let's find out. Add pins. Pins is equal to ultimate load at the pins over allowable or applied. Let it be applied. A small a. Okay, what is this value? Ultimate 39 point. 39 10 point. What is the factor? Okay, don't worry. This is the factor of safety at the pin. Okay, so we found both answers. This is your second answer. Any question we have done for this? This is the factor of safety at the pin. Okay, so we found both answers. This is your second answer. Both answers are done. One answer is factor of safety at the links is 4.1. Factor of safety at the pins is 2.42. Any question we have done for this question? We are moving on to next one. Any question in this solution? You may have to follow carefully to understand, right? Just 2-line answer for this one. You don't have to worry about. Okay, let's solve this one. Are you ready? Okay. All of you keep working along with the calculation. Okay, let's take it as a practice, please. If you have any question, you can stop me anytime. All right? Right? The force applied at handle of the rigid lever causes the lever to rotate clockwise. About a pin B. Where's the pin? The pin B. There's a pin, that's why about a pin B. From here, to start from here is the pin. From about B, it is rotated at an angle 2 degree, making an angle 2 degree. Determine the average normal strain. Now we are going to do the strain. Last time is all about stress and factor of safety. Now is the second factor that we learn, strain. How much the strain in each wire? The wires are unstretched when the lever is in horizontal position. Do you understand the question? You are given with this is the support, right? There is a wire and this is pin and there is a support, wire is hanging, and this is your another support at F, a wire is hanging, and there is a handle. Okay, all these things are at equilibrium condition when no load is applied at E, and as it is stable with the depth at AH as 200, depth at GC as 200, depth at FD as 300. No, sorry. GC and FD are 300 at equilibrium condition or no load is applied at E. When no load is applied at E, it maintains 300 and 300. This is a wire's length. They are flexible wires, okay, steel wires. When a load is applied at E, it will tend to stretch itself, elongate, okay, change in length. The position here is can move to this point. The position here can move to this point, can move to this point. It is a little bit lower down. So how much is the value we are going to find now? You are asked to find, you are given with these conditions, you are asked to find the strain values at each wire. What is the strain value? What is the change in length? What is the change in strain, not change in length, not just change in length. What is the strain at this point? So this delta, if I keep the value, because I want to use the same notation that I use in the class, it is the AH, right? Delta AH, small one, I use the small one, easy for me to write. Delta AH, this is delta GC, this is delta FD, right? So these are the change in length. Okay, let's find out one by one how this is going to vary and how we are going to analyze this member. Any question here? Right. Whether I can remove this one, okay. Given data, write down the given data. Given data. Please work along with me. Are you doing it? All are doing it? Given data, you are given with the members and the depth, original depths are given. Better you write down the original depth, otherwise you'll get confused. Given, write down the original length, that is important. You are asked to find strain means find out the original length first and the point of interest. You are given with this frame, you need to calculate the strains at each wire. The wires are AH, GC and FD. What is the original length of AH and all? L, let it be, if I take the original length as capital L, LAH will be 200. You might write it like this. 200. What is the unit? Mm. Let it be mm. Okay, all mm. Because I'm going to find all in mm. Convenient way. And then what is the length? Right here to save some space. Original length of GC before applying load. Before turning in. Original length at GC will be, how much is it? Anybody? Original length of GC will be 300 also. Okay, you can even put equal to 300 mm, same. Okay, that we must know. And what causes? There is an angle. There is no delta given, but angle is given. Now a simple conversion of angle can give you all the change in value, change in depth conveniently. Right. Let's convert this angle into radians. Or before we do this one, let us draw the diagram first. Okay, diagram, how this is changed. I do it here itself so that it is clear on this diagram itself. I tell you this spot. The angle of deflection will be something like this. About the member, when there is a rotation like this, when there is a rotation, when it is rotated in a clockwise direction, automatically the member will change. AE will change to AE dash or AD dash, AD dash, A dash, D dash. The line will be, let me insert the line. The line will be like this. About, it's going to rotate about, it's better I get the line over it. It will be like this. It will change to, it will be like this. Okay, and the line will tend to rotate like this. Okay, it will rotate above B. Now let's mark the values. A change to A dash position, B is there. C change to C dash. Where is it? C change to C dash, and then D change to D dash. D change to D dash. Okay, put the dotted lines in. Because of this rotation, the position of the wire, position of the member. If I take this as what is written as a handle applied to handle, force applied to the handle of a rigid lever. This is a lever. This is a lever. This is a lever arm. And this is the lever. This is the lever or lever. We can use anywhere. Lever. This is the lever arm. This is the arm. Lever arm where you tend to rotate. Lever arm. Okay. Lever arm. Okay. Now when you rotate it, the lever will change the position from AD to AD dash and E dash. Okay. We are rotating actually. Let it be like this. So change to AD dash actually. You see the differences in the values. What is the angle of rotation given? It is about B. How much is the rotation? How much is the rotation about B? 2 degree, isn't it? Since degree is given, you need to convert to equivalent values. You must know the equivalence of the radians between the degrees and radians. If you convert, you can conveniently calculate it. Okay, 2 degree. The angle of rotation is given. I am marking this one, and then we can solve for the answer. Okay. Okay. Let's take the diagram separately so that it is clear for you. Actually, these values are not useful to you. Okay. For a moment, you have to forget it. Otherwise, you confuse between these. We are not doing any horizontal things. Better you forget for a while. We are only finding the strain. Strain means elongation. And the strain at AF, GF and FD are important. In doing so, you need to find the original and change in length in the members given to this. Okay, answers. Strain, strain value. I mark the strain at this point. Strain at AH, strain at CG and strain at DF. DF, yeah, DF. Okay, these are the values asked. Let's calculate one by one. Okay, start from here. Solution. You must know the variation between, and this is the one of the solution is the free body diagram. I have drawn in the diagram itself. Please make use of it. And then our original length is AD, change in length is A dash, D dash, the change in position. This is the original position, original, this is changed position, okay, right. And then you should know the difference between, one moment, you should know the difference between, the relation between radians and, what is the relation between radians and degree? I think you should be knowing. What is the difference between radians and degree? Any idea? Pi radians equal to 180 degree. Okay, pi radians equal to 180 degree. Because we cannot substitute 2 degree as it is for calculating the values. It is possible by trigonometry, but let's change to radians. You are given with 2 degree, right? So I want to calculate changing 2 degrees into equivalent radians. How do you do it? You use this one. So pi radians equal to 180 degree. How much will be the 2 degree? What is the answer here? You will get in radians. How much is the radians? Give me the answer, please.
0.0241.
Very good. 0.035 or 39. You keep it like this. Radians. This is the value, equivalent value. So I got the value in radians. How much is change in value at this point? Right. Now let's use the formula at each and every point. Solution. The strain at what you're asked to find out? Strain value, correctly. Strain value at, or I just use the formula itself, epsilon. Let's write the formula. Epsilon, what value you need? AH, G, CG and DF. AH is equal to epsilon. AH is equal to change in length to change in length at AH, isn't it? Change in length at AH divided by original length. I don't write for everything. You have to remember, okay? Original length at AH, okay? Original length at AH. So repeat the formula everywhere for all the 3 points so that you can get it. Length at AH, okay? What is the change in length? We need to find out delta A, right? Let it be delta AH divided by LAH. Do you have LA and delta AH? Don't have, right? You need to find delta AH. Delta AH is equal to, what is the value of this one? The radians we found out just now, 0.349. Am I right? Okay, come on, mark here. Okay, we want the value at this point. This is the dotted line, dotted line. Dotted line. I put it at dotted line. Okay. Originally it was at this point, changed to this point by this degree, right? And the original was 200. Changing was this one. Can we rearrange and get it? Can we rearrange and get it? Tan theta, right? Tan theta, right? If you want delta A, mean opposite, you want this one, right? Delta C dash. This is delta A dash. Here. Consider B C dash. Okay, opposite side by adjacent side will be C dash by 300. And then for DF, consider this triangle. This triangle BDD dash. When you consider BDD dash, you will get what is called delta DD dash. Okay, BDD dash. It will be opposite side. You want opposite side will be adjacent side. Tan theta equal to opposite side by adjacent side will be the whole length 500. Okay, whole length 500. Okay, like that we are calculating these unknowns by following these norms, right? Okay. In doing this, we do not remove this one. Let's find one by one this value. How much is this value? If I find one by one, it will be clear. AH is equal to delta AH over original length AH. Okay, I need delta AH, which will be equal to, consider the triangle. If you want, I draw here. Consider the triangle like this. I consider 2 degree. To find what is this value, I take tan theta because theta is already available for me. Okay, tan theta. Why I don't consider tan? Because for my smaller angle, you can smaller and very low slopes, you can just take it as theta itself. Okay, I repeat, tan theta is equal to opposite side by adjacent side. But for smaller angles, you can take it to be theta itself. My opposite side is delta A dash divided by adjacent side is, how much is this? Please find. 200 mm, correct? Please tell me the answers, 200. Hence, I will take my delta A dash. Delta A dash. Let us follow here. Theta in radians, in radians. Radians is equal to, you know value, right? Can you substitute and give me the answer, please? Quickly. 0.034. You're going to find out the remaining, please. 349 times 200. What is that? You can keep 3 digits, okay? You always keep 3 digits. 981 mm. Okay, this is the value of delta A dash. Okay, let's substitute in this equation. I found the strain already. How much is the change in length? Let's find out. Substitute in this case. My value of, after this, maybe I go here. The strain at, just repeat the equation. Strain at AH will be equal to AH delta AH change in length to the original length, which is change in length. Just now we found out 6.9813. 1 you can keep it, and then what is the answer for original length? Original length at A will be LAH will be how much is that? 200, right? 200. 349 mm per mm. Okay, this is strain, right? So the unit will be mm over mm. Just write it like this. Change in length to the original length, all in linear meter. Let's find out the second value. We need to find strain value at CG. Okay, strain value at CG. To find this, same, follow the formula. You know that the strain is equal to change in length to original length. Am I correct? We need to find the change in length by using the trigonometry given to you. The geometry. Are you there? Okay, 300 mm. Okay, let's take the dimensions there. Your dimensions are like this. Let me draw here. You have CG, right? CG is from B. You take this as a B, and this is the lever, and this is the change in length, right? Change in length. You have C dash, okay, C dash, and the angle of this one is 2 degree, right? Width is 300. Let's find out theta. Same as the last time. We take tan theta, or just the theta is equal to 300 is equal to how much is the theta? Given to you need to find out what is this. Original length is how much is original length? It's boring to you. Add 0.03491 is equal to CC dash by 300. Let me find the CC dash. CC dash is equal to 300 into 0.0349. Come on, give me the answer, please. 47 mm. What will be? This is the CC dash, the change in length, right? Change in length, or delta. Say delta. What I wrote the notation. Use the same notation. Delta CG. Okay. Now delta CG is equal to. This is the value. Let's find out the remaining. Delta CG. Can you find the strain? Strain is equal to delta CG divided by original CG. Substitute the value delta CG divided by original. What is the original CG? 300. Can you find the answer? 0.0349. Also the same. A little bit variation only. Okay, first and second, because they are near to the support. Both are equidistant from the support, isn't it? That's why you're getting same. Both the point C and here are at most equidistant from the support. A little bit variation only. That's why you're getting similar value. You should be able to justify your answer. Right, for the third one, I have to go now. To find your strain at, what is the notation there? Let me do it. Strain at DF, right? FD. I use the FD, right? We use FD, yeah, FD. What is the strain at FD? I give the drawing only, please do it, okay? This is B, C at 300, and then another one is at D, is F. I mark this as DF, okay, DD dash, DD dash is equal to DF. This is the value of C. So totally you have 500, right? And the angle of change will be 2 degree. Can you repeat the same answer for the third case? I did 2 cases already. Can you repeat it for the last case? I give you the answer. The answer is strain at DF is equal to 0. Use the same procedure. I'm not giving different one. You can follow the same procedure to answer for value at this point. 82. The answer is 82. Mm over mm also. Okay. 82. Okay, stop here. Any question you can ask me.
Miss,
Yes. The time up already.
we can straight use the degree, right? No need to change to radian, right?
We are using degree because you are comparing with the number, multiplying with the number, isn't it? We are not taking tan. If you're taking tan of the angle, okay, converts already.
But I use degree, 2 degree to calculate still the same answer.
Not much variation, yes, not much variation. But in this case also I didn't change. Yes, I didn't change the degree to radian in this case. Yes. Yeah, you can take it as it is. Any other question? Did I answer? Where is he? Where is he? Martin, did I answer your question?
Yeah.
Okay. Any other question from others? Do you follow the calculation? I post this video again. You please go through. Part of the question will come in your test 1, not all, because it's a repetition of the same procedure to find your strain value for the different arms from the support. I hope you can manage. Any other question for these 2 chapters only? I even hold the 3rd chapter because you have the test. Practice well. Read all the relevant question and answer from your classwork and tutorials, and today's slides also I'll post to you. Prepare well. Anytime you can text me for question and answer. If you are not clear, stuck up, just text me or WhatsApp me or MS Team. You can use MS Team to chat with me. Okay, good luck. If no question, I wait for another 1 minute. If no question, you can take leave.